In this video, we are going to apply information from the last two videos. That was video 317, where we learned about constitutional isomers, and video 318, where we learned about functional groups, and apply both of these concepts toward solving problems. And the example problem we're going to work through in this unit is we are going to go through how to draw constitutional isomers of a particular functional group. Let's tackle this example problem. In this example, we're asked to draw three different ether constitutional isomers that each have the molecular formula C4H10O. So how do we unpack this particular problem? Well, the first thing that I would recommend doing is use the information that we have available in the problem to your advantage, making sure that we're following the directions. So an ether, if we look back at our handout that goes along with the module and that we saw in the video for the functional groups, that was video number 318, we saw that the ether functional group has to have carbon single bonded to oxygen bonded to carbon. And we said in the last video that each of those carbon atoms of the ether can't be a carbon-oxygen double bond. It just has to be carbons bonded to other carbons or hydrogens. So I'm going to sketch that out up here as a reminder that we need a carbon-oxygen-carbon bond as the prerequisite for the structures being an ether. And then we have to have 4 carbon atoms, 10 hydrogens, and an oxygen in these. And we can assume that this formula will allow us to fill the complete octet, because in this class we will not be dealing with molecules that are so unstable that they don't fill the octet. So the way that I would approach this is we have that basic definition of what an ether is. Our molecule absolutely has to have carbon single bonded to oxygen that's single bonded to carbon, so COC. We're drawing 3 constitutional isomers in total. So what I'm going to do to solve this problem and keep myself organized is I'm drawing 3 COC skeletons here, because that's what absolutely has to be present for these molecules to meet the definition of an ether. So that's why I filled in this as the brass tacks absolute minimum skeleton that we would have in this molecule. Now from there we build on the complexity by thinking about ways that we can arrange the rest of the remaining atoms. So thus far we've incorporated 2 carbon atoms of the 4 total, and we've gotten rid of the oxygen because the oxygen is what's required there. So thinking about how can we fill on an additional 2 carbon atoms, because we have 2 so far that are essential to an ether, and then 4 in total, so we need 2 more. How do we plug those in? And what are the possible places that those could go? So thinking about different motifs, we could put a carbon at each end here. That would give us a total of 4 carbon atoms in our C4 formula. We could instead, filling in additional carbons, plug 2 carbons additionally here at the right end of the molecule, like so. That would give 4 total. And then you might be tempted here to say, well, what if we filled in 2 more carbons at the left end of the molecule? The problem with that is that would end up creating 2 structures that ultimately become completely identical, because in the case of this one, you number the longest carbon chain, 1, 2, 3. Up here, longest carbon chain, 1, 2, 3. You would end up finding that these 2 molecules would ultimately be totally superposable, totally identical, and have the same IUPAC name. So that is going to be a no-go there. So what could we do instead? We need to find a way to incorporate 2 more carbon atoms into this molecule. How can we go about doing that? Well, one way to go about doing it is to put in branches, because previously we've just done chains of carbon. So how can we make a branch exist here? Well, if we put a carbon here and then branch a carbon off of here, that would do the trick. And that would give us a grand total of 4 carbon atoms in this molecule. Now that we have the carbon and heteroatom skeleton in place, that is the carbons and all of the non-hydrogen atoms, now what we do to finish this off is fill in all of your hydrogen atoms to make a complete octet on every single carbon atom. So filling these in, 3 hydrogens there on that carbon, 1 hydrogen here, 3 hydrogens up here. I'm just going in and filling in the complete octet for every single carbon atom by adding hydrogens as needed. And if we take a look at filling in all the hydrogens here and we count up the total number of those hydrogens, it should be equal to a grand total of 10, since that's what we have up there in the formula. And indeed it is. So with that check in place that the structure in the lower right-hand corner has 4 carbons, 10 hydrogens, and 1 oxygen, and it has that ether functional group, we can be confident that the structure that we have just shown here in the lower right-hand corner is indeed an ether and fits the definition here of C4H10O. What about the structure in the middle? Well, we're going to do the same thing there. We filled in the skeleton previously, and now we are going to go in and fill in the hydrogen atoms to make all of the atoms fill the complete octet. In the case of the oxygen atom, the oxygen generally has 2 covalent bonds and 2 sets of lone pairs. We haven't filled in the lone pairs here. We could if we wanted to. We don't necessarily have to make a complete structure here. But if we're doing true Lewis structures, we would need those. If we're doing any of the other types of structures like condensed structural formula or line angle formula, we don't need those lone pairs to be included. They're implied that they're there. So in this structure now, with all of the hydrogens filled in where they would go to fill the complete octet and give all the atoms with no formal charges, we have a grand total of 10 hydrogens. So we go with our 4 carbons and our oxygen atom, and indeed we have an ether functional group that we had sketched out there in blue as the starting point of this. So with that in mind, we can check this one off as correct as well. Last but not least, up at the top right corner, filling in the hydrogens as we have done before to give a complete octet on all the carbons. Every carbon gets 4 covalent bonds, not more, not less. Filling those in all the way around, filling in my hydrogen atoms there. Lone pair on the oxygen if we're doing a Lewis structure. If not, it's implied that it's there. Counting up those hydrogen atoms, I see that we have a grand total of 10. That allows this to fit the H10 part of this. There are 4 carbons, and there's 1 oxygen. And indeed, in blue, there is our ether functional group. And so with that, I'm going to put a big red check on that to indicate that that is all checked out as well. Let's do one more example where we're going to take the same theme of drawing constitutional isomers of a particular functional group to test our knowledge here. Here we go. Let's give this example a try. Draw 3 constitutional isomer esters that have the formula C5H10O. I strongly encourage you to hit pause, apply what you learned from our last example problem toward this problem, and then check your answer relative to what I come up with by hitting the play button. So how are we going to draw 3 constitutional isomer esters with the formula specified here? Let's go ahead and bring up our functional group chart so that we can be reminded of what an ester functional group is. Looking at our chart, an ester functional group by definition is represented in this bottom row here as a carbon-oxygen double bond, which we call a carbonyl. And that carbonyl, carbon-oxygen double bond, is directly bonded to an oxygen that's directly bonded to another carbon. So I'm going to fill in a little scaffold here for 3 different molecules that all have a carbon that is double bonded to an oxygen. So in other words, a carbonyl is what we refer to that as. An oxygen bonded here, and then another carbon right here. I'm drawing this as a line angle formula this time. I'm going to do that 3 times because we're supposed to draw 3 different constitutional isomers here. So I'll repeat that 3 times in total, like so. And then from there, I'm going to go ahead and fill in the rest of the atoms to give this formula C5H10O2. With the functional group filled in, that accounts for 2 of the carbon atoms, because we had to have a carbon atom, both at the carbon-oxygen double bond that I've highlighted in blue and over here, in each of these skeletons, or the very minimal form of this. We also have accounted for both of our 2 oxygen atoms in the minimum structure here that makes up the definition of an ester, like so. And now we need to fill in the rest of the atoms. So our oxygens are all accounted for, and we've accounted for 2 of the 5 carbons in total. And as following the approach that we took in the last example, what I'm going to focus on is filling in the rest of the carbon atoms uniquely, and then the hydrogens will generally take care of themselves because the hydrogens inherently assemble in the number necessary to fill the octet on all of the atoms. So to get 5 carbons in total, how can we go about doing that? I'm going to fill in black here, thinking about ways that we could go about doing that. We could extend this over by 1 carbon to here. That would mean that we have 1 extra carbon there at the end of the line, interpreting that line angle formula. That would bring our grand total of carbons, those blue dots, to 3. So then extending it out, this would be carbon 4 and carbon 5 to make up one of the possible constitutional isomers. And I've filled in as blue dots here the 5 carbon atoms in total in that skeletal formula. And if we were to count up the number of hydrogens that we would observe for that structure, should come up to be 10. And looking at it and thinking about what it is, this would be a C3 here, so that's 3 hydrogens. Carbon atom here has no hydrogens because it already has an octet. We would add the 3 hydrogen atoms from here to 2 more here. That makes 5. 2 more here makes 7, and 3 more here makes a grand total of 10, making it fill that formula of H10 pretty much automatically if you're assuming that all those carbons have a complete octet, which they always do for purposes of these types of exercises with stable molecules. Coming down to here, we need to come up with another way to arrange our additional 3 necessary carbons. We have the 2 to start with, and then we need to figure out how to bring in 3 more in a way that will give a unique final structure. Well, one way that we could do about it is to have extended a couple of carbons over here on this left-hand side of the molecule. 2 carbon atoms there versus the 1 up here makes this inherently different than that, because here we had a carbonyl group directly connected to a carbon and a carbon. Here, a carbonyl group directly connected to just 1 carbon. So that's make these 2 groups immediately different. And then to fill in the rest, we've accounted so far for 4 of our 5 carbon atoms in total. So I extend this by 1, and that's going to result in having the final total count of carbon atoms here being 1, 2, 3, 4, 5, giving us the grand formula of C5 with the 5 carbons in blue, H10 with all the implied hydrogens there filling the complete octet, and then O2 in pink. Finally, we come down to here. How do we fill that in possibly as a molecule as C5H10O2 that is unique from the 2 structures that we saw up top here? One approach that we can take to that is we can think about making branches. So let's see if we can do something like that. So we can make a branch here, coming off like that to give an isopropyl group there. That would increase our number of carbon atoms by 2, 1, 2, and there's the carbon right there, and carbon right there. So that gives 4 in total, 1, 2, 3, 4. And then we need a 5th one because the formula is C5. So we put a carbon atom right there. And that would give us 1, 2, 3, 4, 5 carbons in total. H10, if we counted up how many hydrogens would be necessary here to saturate the molecule with hydrogens, and then 2 oxygens here and here. And there is one other possibility that I can think of offhand. There might be another possibility as well, but you could have also come up with a distinct structure where we have our ester group here, and the isopropyl group is over on this side of the molecule, and over here is just a 1 carbon chain. So we could have had 1, 2, 3, 4, 5 carbon atoms. There would be 10 hydrogens if we fully added enough hydrogens in here to fill the octet for everyone, and then 2 oxygens, so O2. And that would represent an additional 4th constitutional isomer. You were only asked to provide 3. And generally, if I'm giving questions like this for any graded assessment, I would specify how many constitutional isomers you're aiming for, because the number of isomers can become quite extensive when you start creating molecular formulas that are relatively complex. And in fact, in this case, I could quite possibly go in and maybe find another possible constitutional isomer to work with here. I can't think of one offhand, but I'm not saying it doesn't exist. So with this problem-solving session, you should now be comfortable with applying the terms constitutional isomer to a variety of different functional groups, including any of the functional groups listed here on this chart from chapter 12, and applying those toward problems where you're given a molecular formula and asked to draw a certain number of constitutional isomers that fulfill those criteria listed in terms of the functional group and in terms of the formula.